Hello, this video tutorial is about problem 3/29. This problem is taken from the book Dynamics by Meriam. It's a sample problem and it has been solved already, and you can see in the picture. The graphics are also visible. There's a sphere body 1 and there's a ground body 2. Sphere is approaching the ground with the speed of 50 feet per second at an angle of 30 degrees. So typically, if there's no effect of coefficient of restitution, the body will depart at the same velocity and at the same angle with which it has hit the ground, that is 50 feet per second at 30-degree angle. But in the presence of, or in the effect, with the effect of coefficient of restitution, which is given in the problem as 0.5, so we'll see that its effect is on the vertical component of the velocity, and the horizontal component is conserved because the coefficient of restitution, the forces involved in this interaction between two bodies do not act on the horizontal component. So the final vertical component becomes 12.5. Initially it was 25 feet per second. So after hitting the ground, the departure vertical component is 12.5. And the horizontal component, which was initially 43.3, remains same as 43.3. So the answers in the problem are, as you can see, visible here. We want to bring the same answers in our simulation done on Simwise 4D. That is, we want to see our departure velocity 45.1 feet per second, and the departure angle should be 16.1 degrees. So now we switch to the Simwise for our simulation of this problem. Okay, now we are in Simwise. So here we first go to the settings, simulation settings here, and then we go to units. Always remember to set units. So we choose English pound as our problem is in English pound system, and the distance will be in feet. Close. Now our simulation settings are done. We don't need to change other parameters. So the bodies involved are a sphere and a rectangular box. We choose sphere on the top right icons here, and then we click anywhere and we stop at any reasonable position. We double click. We go to the sphere size here, the sphere tab, and we put 0.05 as our radius of the sphere, and then we again double click, and then we choose to input the position. First we select 0 along x, 0 along y. This is just the initial position so that everything is at origin. Then we choose another icon to create a box. We create a box here, and we double click, and also we select its position as 0 along x, 0 along y, and 0 along z. Then we go to the box tab to select to input its sizes. So width is along x-axis, which is basically we want to have 10 feet, would be a reasonable estimate, and then length, which is along y, we chose at 2 feet, and the height we keep it as 0.05. So here we are. And as you can see, centers of both the objects are at origin. So now we again double click the body and the spherical body, and we raise the body along z-axis to say 0.5 feet. So now it has a reasonable position. Then we rotate the camera so that we can see the right view, pressing R. Next we go to perspective view selection, and we choose isometric selection so that it perfectly, the problem is represented in the same manner as given in the Meriam's graphics. Problems graphics are matching. Okay, now we have to fix the ground, otherwise gravity will act or the force will act and the body will this will also be a floating object. We fix it, so our ground is now fixed, and the sphere has to be given initial velocity. As we know that our problem has two components, 43.3 and 25, along x-axis and z-axis respectively. So here we give minus 43.3, y minus because our positive x is in the opposite direction. And the vertical component is minus 25. Again, minus is because the z positive is upward direction. The ball is being hit downward. We apply, close. Then again, let's not forget that the gravity has to be turned off because in the original problem there is no mention of gravity. So we again go to simulation settings. We go to gravity and switch off. And now you can see the problem is almost there. Uh, if you like, we can see how it is running. But one parameter that we have to set is we have to set the two objects, selecting both the objects by pressing Control and select the two objects and click right click and set to collide. This is very important because otherwise they will not collide, and the ball, when it will have some velocity, it will just pass through this plate. Okay, we are almost done with everything. We just press the play button, and the problem was so fast that we could not see. So we again go to simulation settings, and we go to the top. In the top of the settings we have integration, and here we choose I would suggest 0002, 0.0002. So now our problem is reasonably slow, and here you can see it is going like this correctly. Then we'd like to see the velocities of this sphere. We select the body from the left icon, left browser icon, insert meter, and insert velocity. So now we have so many components of the velocity available, 3 x, y, z, and the resultant is in the modulus of velocity. We right click and change display to digital. So we'd like to see the values. When the problem is initiated and it does not rebound, the object has just hit the ground. So you can see the initial values of the velocities, initial velocity x component and z component are perfectly the way we had input already as initial conditions. Now, if you drag the slider, and then you can see after hitting, the new components are 30.3 or x component and 12.5 the vertical component, and the resultant is 32.8. Obviously these values are not matching with our sample problem result or the answers. The reason is that there's one more variable to be set. We go to the bodies, select them simultaneously by pressing Control, and then go to properties, and in the material we have coefficient of restitution as zero 0.5, which was required as a basic parameter of the problem, and the friction coefficient should be 0. And now if you see here, if you play, so the approaching and the departure values are available. As you can see, Vx is horizontal component is 43.3, which was previously 30. So now it is 43.3, which is perfectly the same as approaching angle. Now the departure, approaching velocity. So departure velocity is same, and the vertical component has been reduced. So our final velocity is 45.1. So with these two components, as you can see perfectly, they are matching with our original problem statement or the answers. Hence the problem is well simulated. Thank you.